The goal of this video is to learn about the different states of matter you may see when working with acids and bases. We will also learn how the two theories, Arrhenius and Brønsted Lowry, define what acids and bases are. Let's begin by looking at the different ways substances, or should I say states of matter, can be represented in chemistry. The states of matter are represented using parentheses: S for solid, L for liquid, G for gas, and AQ for aqueous, which, by the way, it means a substance is dissolved in water. What makes solids, liquids, and gases different from aqueous state is that they are in their pure form and are not dissolved in water. For example, the liquid state of mercury is different from an aqueous state because it contains only liquid mercury and is not dissolved in water. In contrast, the sodium chloride, shown here, is aqueous because the salt is dissolved in water. Now that we understand the different states of matter, let's look at how the Arrhenius theory explains acids and bases when they are dissolved in water. So, according to Arrhenius theory, an acid is a compound, also known as a substance, that breaks apart and releases hydrogen ions or protons when dissolved in water. Let's take, for example, hydrogen chloride. When hydrogen chloride gas dissolves in water, it releases hydrogen and chloride ions. Because it releases the hydrogen ions as a compound dissolves, we consider it to be an acid. Once dissolved, by the way, in water, it is now called hydrochloric acid. So in summary, according to Arrhenius theory, if you place a substance and that substance is able to release hydrogen ions, it's an acid. A base is a compound that breaks apart and releases hydroxide ions when dissolved in water. The example here that we have is sodium hydroxide. It breaks apart and it releases ions. The part that we call the base is the hydroxide. So the biggest thing to remember about Arrhenius theory is that it only works when the substance is dissolved in water. Therefore, the Arrhenius theory has limitations because acid-base reactions can happen without water and in different states of matter. This is where the Bronsted Lowry theory allows us to explain acid-base reactions that do not always require water. To make this idea easier to understand, let us use a simple analogy. Think of Barney. Barney donates a book to Lowry, and Lowry accepts that book. Similarly, an acid is a compound or substance that donates a hydrogen ion or proton, while a base is a compound that accepts a hydrogen ion or proton. In this chemical equation, we can see hydrogen fluoride gas donating a hydrogen ion to ammonia base. Our products include ammonium ion and fluoride ion. Ammonium is considered the conjugated acid because the species is formed after the base gain a hydrogen ion. Remember, in the reactant side, it accepted the hydrogen ion from hydrogen fluoride. So it went from NH3 to becoming NH4 plus after accepting the hydrogen ion. And our fluoride is called a conjugated base because the species formed after the acid lost a hydrogen ion. Remember, it was originally HF, but it donated the hydrogen ion, so the product became fluoride. By looking closely at the states of matter, notice that in the first example, the acid is a gas. However, in the second example, the acid is a liquid. And in the third example, the acid is aqueous, meaning it is dissolved in water. This shows that Bronsted Lowry acid-base reactions can occur in different states of matter, with or without water. Looking back at the second example, we see acetic acid donating a proton to ammonia base. The result is acetate ion and ammonium ion. In the fourth example, we see hydrochloric acid donating a hydrogen ion to water. The result includes fluoride ion and hydronium ion. Hydronium is produced after a molecule of water has accepted a hydrogen ion. It went from H2O to H3O plus. In summary, Arrhenius acids release hydrogen ions and bases release hydroxide ions, both occurring in water. In contrast, Bronsted Lowry acids donate hydrogen ions. And bases, they accept hydrogen ions, which can occur with or without water.